Hey, welcome back. In this video we are going to talk about some advanced exercises about alkenes and alkynes. There are two types of them. The first part of the video will be some exercises that you have to do synthesis, like start from a single product and go to another single product through several steps. And the second scenario is that you have a hidden compound and you are going to find that, or more than one hidden compound, through some reactions that hidden compound gives with some specific reagents. Without any further ado, let's dive into it. Let's start with the first example. Here we have to find the reagents that we need to carry the following steps. Let's start with the first one. Here we have the addition of two carbons, and the type of the reaction that has happened here is alkylation. So in order to add two more carbons to a triple bond, the terminal triple bond, first we have to treat with a strong base. And the second step was alkylation. How many carbons do you need? 1, 2 carbons with a primary alkyl halide. Let's move to the next step. Here, in order to reduce the triple bond to double bond, we have two options, Lindlar catalyst and lithium ammonia catalyst. Lindlar catalyst made possible the reduction to the double bond from the triple bond in cis. So as you can see here are two hydrogens that are not normally written, but I'm writing them for clarification. And you see that the double bond is on cis, which means that the proper catalyst here is Lindlar, hydrogen Lindlar. Not lithium in ammonia solution because it gives a trans product. Okay, let's move to the next step, that is converting a double bond to a cyclopropane. In order to do that, there is a typical reaction that is called Simon-Smith reaction that uses a carbanoid that is formed by the reaction of diodomethane with zinc copper mixture in ether. It's going to yield a cyclopropane. Okay, let's start with a second example. Here we have a conversion of a double bond to an aldehyde group. Benzylic is not touched. It requires more than one step to carry out this synthesis. My advice in this kind of synthesis that requires more than one step is to go reverse. So on this way, the synthesis. Okay? Now, from the aldehyde here, we can go backwards to benzene ring is untouched to a triple bond. From the knowledge of alkynes, we can treat a triple bond with hydroboration oxidation and yield from terminally alkynes an aldehyde. Okay? So from triple bond, in order to go to the double bond, there is no single step. But we know that from triple bond, we can go to a halogenated product that is this one. Okay? And if we treat a halogenated product with two equivalent of potassium hydroxide in ethanol, we can go to the triple bond. Okay? And if we treat a double bond here now with an halogen in the presence of dichloromethane, you're going to yield a halogenated product. Okay? So 1, 2, 3 steps to carry this synthesis. Let's move to the third example. Here, as you can see, you have addition of a methyl group to the double bond here. Okay? In order to do that, it is possible only by the alkylation of the triple bonds, with what we have learned up until now. Now, to do alkylation, you have first to convert this double bond here to triple bond. So the reverse step, first step, is going to be this one. And to go from triple bond here to the double bond here, it requires a reduction, but not a complete reduction. And in order to do partial reduction was Lindlar or lithium in ammonia. As you can see here, the reduction is done on trans because you have one hydrogen here and one hydrogen here. In order to do trans reduction from triple bond to the double bond, you have to use lithium as a catalyst in ammonium solution. Okay, not hydrogen with Lindlar catalyst. Okay, because it's trans. If it was cis like above, you should have used hydrogen with Lindlar catalyst. Let's move now to the next step. We have to add this metal group here. How we can do that? We can start from a triple bond, terminally triple bond, and first treat that with a strong base, such as sodium amide. And the second step was the addition of the alkyl halide, a primary alkyl halide. Number of carbons depends on the number of carbons that we need here. We need only one we add here. Now, from triple bond to go to the double bond. As we saw previously, we cannot go straight forward, so first we have to do an halogenation. Okay? And we can do halogenation to the double bond to yield halogenated product. And from here, we need to equivalent of a strong base such as potassium hydroxide in ethanol. Okay. Let's move now to another type of exercises in organic chemistry that are harder to do. Now, it is given the compound A, that is C9H12, and it reacts completely with 3 equivalent of hydrogen and yields a product B, C9H18 in palladium. Now, the compound A goes ozonolysis and yields a cyclohexanone, like this one, plus other products. And the compound A, when it's treated with a strong base and the addition of halogen, is going to yield this product, C12H14. Who is A, who is B, and who is C? In order to solve this kind of problems, the first thing that should come in your mind is DOU, or degree of unsaturation. The first thing that you have to mind, that should go in your mind, because by knowing the degree of unsaturation, you can know if there is any ring present, how many double bond or triple bond are present. Like, for example, in this case, we have this formula. So what we are going to have, 2 multiplied by 9, minus 0 halogens, minus 12 divided by 2. This is going to give 4 degree of unsaturation. But this compound here can react fully with 3 equivalent of hydrogen, but it has 4 degree of unsaturation. 1 degree of unsaturation, keep in mind, if it's not reduced by the hydrogen completely, if it's not reduced by the hydrogen, it tells us that contains a ring, because what hydrogen can do to a ring, okay? A saturated ring, I mean, not a double bonded ring, otherwise it will work to reduce a double bond if it has. Okay, so remains only 3 degree of unsaturation that are supposed to be double or triple bond, depends. We will see. So now we have by ozonolysis that the one product is cyclohexanone. So this cyclohexanone contains 6 carbons, okay? And ozonolysis to yield cyclohexanones here should have been a double bond, because if it were a triple bond, it was impossible. And the point is that the addition here of this metal means that this compound should be a terminally alkyne Otherwise, this reaction would not work. So here we have a double bond in order to yield a cyclohexanon, because if it were a triple bond, it was not possible to connect a triple bond here. And here tells us that should be a terminally alkyne, the compound A, I mean. So what is the supposed structure? The supposed structure, let me write it here. First, we have the 6-ring member, and here should contain a double bond, and it has 6, and we have to add also 3 carbons, 1, 2, 3 carbons. Since it has the possibility to do alkylation, should have a triple bond here in order to form a terminally alkyne. Okay, let's fill with hydrogens. And this is the compound A. What about the compound B? Simple. 3 equivalent means that it is going to remove double bond here to convert that to a single bond, and triple bond here to convert them to a single bond. So the compound B is going to be a totally reduced hydrocarbon. Okay? Now the compound compound C. We can find also the waste here if you want, because this is going to yield, since it has a hydrogen on this side, because this is going to break, okay, and since it has a hydrogen, from the double bond knowledge, from the alkane knowledge, we know that this is going to yield an aldehyde, and on the other side is going to be a carboxylic acid, because this breaks, plus CO2. Okay, for this one converts to CO2 if we deal with triple bond. Now the compound C means that this one here, that was the compound A, is going to react with this one, sodium amide, and an halide, metal halide. So what is going to be the compound C? Addition of another methyl group. Okay, this is going to be the compound C. Let's move to the next example. Now here we have a compound A that has 12 carbons and 8 hydrogens and reacts completely with 8 equivalents of hydrogen in palladium catalyst. And this compound A, if we do ozonolysis, gives these two products. Find the compound A. Now, as I told you, the first thing that you have to do is to find the degree of unsaturation. For this compound, let's find it. It contains 9 degrees of unsaturation, but it reacts only with 8 equivalent of hydrogen. So this tells us that it must contain for sure a ring. Otherwise, it does not make sense. So it must contain a ring. So what we are going to do now? Now we have the formation of these two products by ozonolysis. We see that we have the formation of carboxylic acids. This tells us that on those sides has to be triple bonds, because ozonolysis with triple bonds gives carboxylic acid. If it were double bond, it's going to give another product like aldehyde or ketone. So the ring should be something like this. This is going to connect here, and this is going to connect here. Okay, let's write the ring. How many carbons do we have? 1, 2, 3, 4, 5, 6. We have 6 carbons, but we have 12 carbons here, which means that we have double the amount of carbons to add. Two of this in order to do the equivalence with 12 carbons here. So one carbon. And now we can place the triple bond and the double bond. Let's place a triple bond here. Now two carbon moves away, and let's place another triple bond here, and 1, 2, 3, 4, another triple bond here, 1, 2, another triple bond here. Okay, so 1, 2, 3, 4 triple bonds. Kind of makes sense, because if you break this one here, and this one here, and this one here, and this one here, it's going to yield two carbons here and two carbons here, two of these. 1, 2, 3, 4, 1, 2, 3, 4, 4 carbons here. So it's going to yield this one here. So let's fill with hydrogens. Okay, this is the final product in this case. Okay, let's move now to the heaviest example. We have a compound A that contains 9 carbons and 12 hydrogens. It reacts completely with 3 equivalents of hydrogens to yield a compound B with 9 carbons and 18 hydrogens. First of all, as I mentioned above, you have to find the degree of unsaturation by this simple formula in your way that you want. It doesn't matter if it's this formula or other ways. So is going to give 4 degrees of unsaturation. Okay? But this tells us a lot, because it reacts only with 3 hydrogens. But what about 1 degree? This 1 degree of unsaturation must be a ring. So this compound, from this degree of unsaturation, we make sure that this compound first has a ring. Doesn't matter how many carbons this ring has. The other parts will help us to understand that. So now, if the compound A is going to react with a mercury catalyzed reaction, as we call our hydration of alkynes, this tells us that this should contain an alkyne, so this should contain a triple bond, but in which position? Let's check what it gives. It gives a ketone C and ketone D, and C and D, exercise said, that are isomeric compounds. This reminds us that if it contains a triple bond, this triple bond, in order to yield 2 different products that are isomeric, means that should be an internally triple bond, not terminal alkynes, sorry. Because terminal alkynes is going to give us only the Markovnikov product, single product. If we treat compound A with potassium permanganate, it gives acetic acid or ethanoic acid, as you can call it, plus compound E, that is this structure here, that as you can see, 1, 2, 3 carbons, 1, 2, 3 carbons, 1, 2, 3 carbons. It's a symmetrical structure. It tells us that you have the formation of acetic acid. So this should have been formed because potassium permanganate gives carboxylic acid if it's used to treat an internal triple bond. So in this case, these 2 carbons should stay in the end. Okay? Now, before these 2 here should be on this side here should be a triple bond. Okay? 2 carbons. Now, by looking at this structure, we should have the formation of a ring. But how many carbons this ring should have? So if this ring should have 1, 2, 3, 4, 5 carbons, something else to remember here is that, as you can see, there is a lot of confusion here. Why? Because triple bond, when it reacts with potassium permanganate, yields a carboxylic acid. Okay? Internal triple bonds. But also, double bonds yield with potassium permanganate carboxylic acids if it were an internal double bond. What this means, if we connect this carbon here with this carbon here to form a 5-ring member, okay, and this branch here has to be 2 carbon, 1, 2, 3. Let's count, for example, on this side, 1, 2, 3. The branch should be here, 1, 2 carbons away, okay? And in order to yield this symmetrical product, we have to have a double bond here. Okay, one, 2, 3 carbon, 1, 2, 3 carbons. Okay, so 3 carbons. If this breaks, this is going to give us this product, but we have to fix something here, because when this react, so the compound A, because we are building the compound A here, react with potassium permanganate, yields an acetic acid, and plus this yield these two fragments, acetic acid and this compound here. So we have to add acetic acid here in form of a triple bond, okay? And here needs 2 hydrogens, because if this breaks, also this breaks. As you can see, this side here gives this symmetrical product. This side here gives the carboxylic acid. This is the final structure of the compound A, okay? Now, compound A, if it's react with 3 equivalent of hydrogen, as you may guess, is going to reduce the double bond here, 1 and 2 of the p bonds from the triple bond in order to form a saturated compound. Okay? What about these 2 ketones? These are simple, because this is going, mercury catalyzed reaction is going to impact only the triple bond, and as you can see, is an internal triple bond, so it's going to yield a ketone like this, and another ketone like this, which are symmetrically, okay? Thank you so much for watching, and see you in the next video. Peace.